I also want to just take a moment to thank today's team that was instrumental in putting together today's event. Of course, our guests, Marissa and Jarika, who's a data engineer and a wonderful part of our CloudTrack volunteer team, and Nydia Medina, who's the CloudTrack lead evangelist and is just a pleasure to work with and always really helping put together really lovely campaigns for our social media. So thank you all for your efforts in making this happen. And I'm going to just introduce our speaker, Marissa Fisher. Marissa is a principal engineer at the Broad Institute of MIT and Harvard. And here are a few fun facts about Marissa. Did you want to carry on from here, or would you like me to share your fun facts for you?
Sure, I can take it from here.
Okay.
Yeah, thank you so much for the introduction, and really thankful to be here with Women Who Code, and especially in the cloud track. So yeah, thanks for putting this all together. Just to introduce myself a little bit more. Yeah, I work at the Broad Institute, which is based in Boston, Massachusetts. But I'm originally from Canada, and I guess a question I get a lot is, oh, you're from Canada, you speak French. And actually, I don't. We often learn from a young age, but when I moved to the US, I picked up Spanish instead. When I'm in Boston, you usually find me running on the Charles River or at a concert. There's a pretty good music scene there. And fun fact about me is that last year, so 2023 now, this, yeah, we're in the new year. I took up birding as a hobby, and I own 2 sets of binoculars. So if you want to talk hummingbirds, I'm your girl.
I'm
All right,
gonna
so
stop
yeah,
sharing so you have the
yeah,
power.
let's do that. Perfect.
Okay.
All right, how are we doing with that? Oh,
Looking good, but we're in the middle, so.
yeah. Let me see here. I didn't want full screen mode.
Just click the first slide and then you can go back.
Okay. Can you see just the agenda now?
Yes.
Okay, great. All right, so yeah, what I'm gonna go over today, I'm gonna do a little introduction about the Broad Institute and what our polygenic risk initiative is, and the system that I worked on to support that initiative. And also dive deeper into what kind of resources we chose, overview of cloud functions and cloud tasks, and also best practices for storing patient data, which is a pretty big concern in the industry I work in. Also how we set up the different architecture or pieces to make up the architecture, and also how we do our deployments. And some of the tooling we use around that, and hopefully finish off with some time for some Q&A. So yeah, so the title of my talk today is Empowering Patients with Access to Genetic Disease Risk Scores Using Google Cloud. So I saw in the chat, there's a lot of folks using AWS, some using GCP, some using Azure. So I'm hoping this talk, will be helpful for you regardless of which cloud platform you're most interested in. I think, I've seen among them that there's a lot of similarities in resources and services offered, which is pretty nice. So it's not so difficult to jump from one to the other. And of course, I want to thank the Broad Institute, where I work, for providing the platform for the connection between our laboratory and the eMERGE network, which supports this research project, which is also a clinical initiative, and of course Google Cloud, which we decided to use that provides us the tools and support to make all this technically possible. So a little bit about the Broad Institute. So the Broad Institute of MIT and Harvard is a nonprofit research institute. It's based in Cambridge, Massachusetts, and it convenes a community of researchers across disciplines and partnering institutions. So that includes a lot of the hospitals around the Boston area, different universities in addition to MIT and Harvard, also industry partners and government groups as well. And our mission really is to better understand the roots of disease and narrow the gap between new biological insights and impact for patients. I specifically work within the genomics platform, and within our platform, we need to support a lot of informatic initiatives due to the immense amount of genetic data that we're producing. And that goes towards different research and clinical projects. So a little bit about polygenic risk, or PRS, which is something you might hear me say a few times during this hour. So we got a grant back in 2020 called eMERGE4, and the initiative was to collect samples from about 25,000 patients, so 20,000 adults, 5,000 children. And our focus was to deliver polygenic risk scores back to these patients. And I guess depending on, where their sample was taken, whether it's a hospital, clinic, etc. And we're going to provide these polygenic risk scores for 10 different conditions. But first, what we're really doing is adding a polygenic risk determinant to an overall genomic risk assessment. So this is a nice picture of kind of everything that goes into an individual's risk for a certain disease. So starting with things like clinical determinants. So for the case of, let's say, coronary artery disease, has that patient had an incident, a coronary incident in the past? With family history, do they and have someone in their family who's had an incident before? There's also things like monogenic determinants. If we think about perhaps breast cancer, there's the BRCA1 gene, which is a clear indicator for risk of developing breast cancer. And there's also things like social determinants. So, your lifestyle, exercise, diet, perhaps things like the air quality of where you live. So what we're adding to the picture is these polygenic determinants. And so what that means is really there are different regions in your genome that can increase your risk for developing a certain disease. So unlike monogenic, where it's often a single point mutation or a single change in your DNA, polygenic means many. So there could be a lot of different regions, and we try to look at those regions and sequence for that in our laboratory. And yeah, so then we end up with genetic data that then we need to convert into a risk score. And just a little bit of history on polygenic risk. So this was a study done back in 2018. Done by Amit Kara, who was a cardiologist working pretty closely with Broad for a while. And what they found out was that the higher the polygenic risk score, so let's say for cardiovascular disease in this instance, if you're in the 90th percentile, it means it correlates strongly with the prevalence of coronary artery disease, actually. So another interesting thing here is that actually it's much more common to have a polygenic risk for a cardiovascular disease than monogenic. So we see there's 1 in 12 people have a high polygenic risk as opposed to 1 in 200 having a monogenic variant that can change that. All right, so that's, a little bit of biology. And now I guess I'll get more into the technical side of things. So based on, what the clinicians want to do and the sort of medical reasons for doing this. Well, for myself and my team, our task was to create a cloud system that could allow polygenic risk reporting. So we knew initially that it was going to be pretty low scale. So it was, only 25,000 patients over about 3 years. However, it needed to be highly secure because we were going to be collecting patient data. We wanted to design the system for low cost. And we also needed some kind of interactive data review, because when it comes to releasing clinical results, we usually require a clinical director to look those over and make sure that everything's okay before that gets back to the hands of a patient or a physician. So one of the challenges that I posed to myself and the team was, given this low scale and kind of an opportunity to design a system in this way, how lightweight of a system could we really create to meet our needs? So I guess next then we had to figure out what were those needs. And we came up with these kind of 5 high-level requirements. So the first being that our system needed to be able to interact with third-party APIs. We also needed a way to link the scores to patients. So when the data comes out of the lab, it's really just connected to a sample ID or barcode. And we needed to have a way to connect that unidentified sample back to an actual patient. We also needed to generate reports. So our outputs of this system were going to need to be a PDF report that details some things about polygenic risk, what the patient's risk was, if any, for any of the 10 diseases that we covered. And some of those that we do cover are asthma, breast cancer, I think 3 or 4 cardiovascular related diseases like atrial fibrillation and coronary artery disease. We also look at type 1 and type 2 diabetes. So there's quite a variety of diseases that we look at that could come back on a patient report. So we needed a way to communicate that clearly, and in a format that is, nice to receive, whether it's going to patients or physicians. And we also needed a way for our clinical director to review and sign off on the results. And lastly, we needed a way to deliver those reports both back to third-party APIs and to store that data within our own data storage resources. So a first pretty obvious choice for us, since we had decided from the beginning we were going to use GCP, was that we were going to use Cloud Functions for some of this functionality. So why Cloud Functions? Well, they have a lot of nice features. One being they're serverless, so there's no need to manage servers. You can really just focus on your code. In our case, we're using Python, so focus on writing Python functions and deploying that code to a cloud function is a pretty nice way to work. They're also really good for short-lived spurty tasks, so they can scale up and handle the load as needed. They're also event-driven, so they can react to an HTTP request, very similar as an API would, or they can also react to something like a CSV file landing in a cloud storage bucket. They're also very cost efficient, and you only get charged for what you use, so it's about 16 cents per minute of use. They also have a seamless integration with other Google Cloud services, which was going to be essential for us because we were not going to design a whole system only using Cloud Functions. And they're also very easy to incorporate with continuous integration and continuous deployment processes, which was essential for us in the way that we wanted to be able to deploy our code into different environments and especially production. And you also get logging and monitoring out of the box, which is awesome. There can be some costs associated with that, but you can also control what you're logging. And of course, you don't want to log everything, but the fact that you can simply write a print statement or use the cloud logging library and get that right away is pretty nice. We did have some challenges though, of course, with any resource, there's challenges. So there is a 9-minute runtime limit and a 16 gigabyte memory limit. So we've run into both of these issues, and I'll talk a little bit about that later, but especially if you're trying to use one cloud function to kick off maybe many other cloud functions, that can eat up a lot of memory. And that's an issue that we ran into. And the way that we solved that was to bring in another resource called Cloud Tasks. And this is a really nice tool. One of my colleagues came up with the idea to use it, and I'm really glad she did, because it's pretty neat. I think some of the key features that really helped us was that you can distribute the task orchestration. So you can say, okay, let's send the reports out first, and then we're going to send back to data store, even if that task is going to be hitting similar or the same cloud function later on. You can also queue your report uploads, in our case, report uploads and data uploads. So once one cloud function finishes, we can have the next one queued, or you can have them overlap without eating up that memory within a cloud function task itself. They also integrate very seamlessly with cloud functions. You get nice retry and error handling. You can configure that as you wish. It's also very, very low cost. So it's 40 cents per million operations, and we have not even hit that yet. So technically for us, it's been free. There's some other benefits that we don't take advantage of in our system, but things like sending asynchronous notifications. So you can have the cloud task send out an email to your team, and that doesn't have to be part of the actual Python code of the cloud function. You can also schedule tasks for a later time, and you can also pause them in the console at any time. Another thing that we had to think about was how to solve PHI storage. So PHI is patient health information. And because we were going to be working with patient data, we had to come up with a way to securely store it. So I think the first thing to think about was, well, what kind of data are we going to be storing? And the files themselves, it was not really complicated. So there's CSV files containing the genomic data, there's JSON files, and PDF reports. So none of these really suggested to us that we would need a database. So we decided that there was going to be no need for a relational database in our system, and that was going to save us a lot of development time and money, because relational databases can be pretty expensive. And what we decided was to just rely on the third-party API that contained the patient information, like names, date of birth, etc., and only pull that information when we actually needed it towards the very end of the process to generate those polygenic risk reports. And I think this was a really nice decision. I'm looking back, it's been a few years since we started this initiative, and I'm glad that we did that. Of course, there's challenges with third-party APIs, I think, which I'll talk about a bit later too. But it's nice, I think, to follow the best security practice in general of storing the minimal information that you need. So overall, this is sort of what we ended up with as our architecture. So I really just wanted to emphasize kind of how some of these cloud resources interact and where those things can happen. And hopefully, that might help you in thinking about how to design cloud systems in your own work. So these ones with the dots here represent cloud functions, and this is a cloud task. So what you can do, like in our scenario before we were using cloud tasks, we were trying to use this first function to kick off like hundreds of the second function down the line. So cloud tasks is a really nice intermediary, because we could space those out without eating up too much memory or time within the first cloud function. Another instance of connecting a cloud function to a cloud storage bucket. So this cloud function generates the PDF and JSON reports that we need to send out. and it eventually stores them in a cloud storage bucket that's secure and dedicated for that purpose. And then we also send that data back through a third-party API. I did mention also, right, that we needed to do some kind of data review, and for that case, it does require a UI. I think, we were all backend engineers, so we wanted to do kind of the most low-key thing we could possibly do to avoid writing JavaScript and HTML and CSS. So what we decided was to use a combination of Cloud App Engine, Firestore, and Google Sheets. And this was really neat. A lot of work went into this. But essentially what it is just linked to an interactive spreadsheet where the reviewer can go through and click either yes or no in the checkbox of saying the data looks good or not. And what they're looking for is things like failure reasons of why maybe the polygenic risk score was not did not come out from the lab or from our post laboratory analyses. And for instance, like if a set of samples came back and every single person was high for asthma, that would be a little bit weird. So they want to look for things like that. And so then getting to deployment. So our aim was to have our system be completely continuous integration, continuous deployment, I guess, compliant, might say. And to do that, we use two main tools, one being Terraform and one being Cloud Build. So I'm actually really curious if anyone here has used Terraform with their whether they're using Azure, AWS, or GCP, because I think it supports all of them now. So if anyone minds commenting in the chat if they have and maybe what they think of it. No users yet. Okay. Dabbled. Couple dabblers. All right. So here's going to be my plug for Terraform. I would highly, highly recommend anyone who deploys cloud resources to use it because it has saved me so much time, and especially the effort of deploying resources across different environments and not having to click around in the console. So I think one of the best things for me using it is that I can, with a couple commands in command line, create an entire project in a given environment and then do that again for another environment. So, I think often we're working with sandbox environment, development, QA, production, and having to go through the cloud console and click around to create every resource that you need and not make a mistake is painful. So Terraform comes in as a really nice resource for that. So I'll show an example in the next slide of how that works. But basically what you are doing is having your infrastructure as code. So you take, I guess, a little bit extra time at the beginning to write out in the Terraform compliant format of what resources you want to deploy. And then you're able to do that in the command line. And so then the other tool that we use is Cloud Build. I think probably most people using GCP would be familiar with that too. And we liked using Cloud Build for things that are frequently changing. So things like Cloud Functions, because that's your code that's your business logic essentially, and where your code lives, right? So something like a cloud storage bucket is not going to be changing very often, or your project name or your IAM permissions. So those things we would put all in Terraform, and then things that could be changing on a weekly, monthly basis would be our cloud functions, and we use Cloud Build for deploying those. So when we want to make a change, let's say we're going to, add a new logging statement in one of our functions, we write that out, push it to GitHub, get approval from another colleague, And when we merge that into development, Cloud Build kicks off and deploys that Cloud function to its develop environment. All right, so yeah, going back to Terraform, this is a really nice example, just how to create a cloud storage bucket. So what you're doing initially is giving it a name and saying what kind of resource it is. So you can do this for any Google Cloud resource, and I think for AWS and Azure it would be the same. You say what kind of, in this case, it's a Google storage bucket. I'm going to call it the PRS reports bucket. I'm going to tell Terraform what project it belongs to. So if it's my dev project, maybe it's emerge-dev. I'm going to give it a location, also a storage class, and also other things like, are we allowed to destroy this bucket? Are we going to put a retention policy? Is there going to be a life cycle rule? In our case, we set retention policies for 1 year in our test environments because we don't really want to keep that data around unnecessarily. So yeah, I would definitely recommend trying out Terraform and checking out some of these features. We've gotten it to a point that we actually even create our project with Terraform, but I'd recommend maybe just, you still create your projects perhaps in the console, but trying out using Terraform for something like a cloud storage bucket or maybe for a pub subtopic, if you use that. All right, so ultimately, what kind of system did we end up with then? Well, the system did end up being pretty lightweight and low cost, so I think that was a success. Our production system still costs to this day less than $6 per month. It's a system that has very little PHI interaction, and there's no expensive bulky database, which I was really glad to avoid. And this was my first time working on a big project at the Broad where we didn't use a database. And I kind of thought at the beginning, no, there's probably going to be a point where we're going to have to introduce this. But I think with such little data and the fact that we had access to a third-party API holding all the data that we needed, it would have just been a lot of replication unnecessarily. We also have a very lightweight UI. There's no JavaScript and no CSS, just HTML and Python, which backend engineers were very happy about. It's fully CI/CD. And of course, there were some issues with Cloud Functions, and then we use Cloud Tasks to work around that, which is a really nice solution. And I think one big challenge, perhaps the biggest, is that when you do rely on third-party APIs for retrieving data, there can be days where maybe that system is down, or instead of taking 3 seconds to respond, now that their API is taking 30 seconds to respond for a single call. And that can really eat up time in your system and throw things off. So we've had to deal with some issues like that. But overall, we ended up with a novel framework that supports a new class of clinical tests. And eventually we had to get this data back, right, to the patient. So this is an example of what the report looks like. And they will receive just an indication if they are high for any particular condition. So this is an example, a test example where the indication was high for asthma. And what this can do then is serve as a guide and conversation with their doctor to make educated decisions about how they can take care of their health now and both in the future. So in the case of perhaps coronary artery disease, maybe the patient isn't showing symptoms for this, but they might want to get on some kind of preventative measures, or if they are having some kind of symptoms, but maybe not fully fledged, they might want to start a medication earlier than later. So it can affect your lifestyle in the moment, and being aware of these things to take steps to prevent or change that. All right. So ultimately, yeah, none of this would be possible without the eMERGE network, the participants that are volunteering, and the consortium. So thank you so much to all of you for being here today. And please feel free to connect with me on LinkedIn if you're interested in anything about the Broad or GCP. I'm happy to talk about both. And yeah, no, I'd love to accept some questions if we have time for that. So thank you.
Thanks, Marissa. Do you want to stop sharing your screen and then we can
Sure.
transition to Q&A, and then I'm going to invite uh, Jarika back up. I have a question in the meantime. I wanted to ask about the third-party API that you mentioned. I don't know if that's proprietary information, but could you elaborate a little bit further? Because that seemed like a really creative solution to dealing with the privacy issue. Yeah, can you elaborate? Is it proprietary, or is it something that is well known or?
Sure. Yeah. So it's proprietary actually to one of the universities that's part of the eMERGE network as well. So the Broad, we were the sort of send out laboratory for this, but then there was also a university which was responsible for providing that API. So it wasn't internal to Broad, it was, yeah, external, but we worked very closely with them to set everything up. And yeah, so they are kind of the patient data warehouse for everything.
Gotcha. Okay,
Yeah.
and could you also talk a little bit more about some of the challenges you dealt with using that API?
Yeah, I would say timing is a really difficult thing, especially because we chose to use Cloud Functions. So even at the end of last year, we had some issues where we suddenly we're just receiving much longer response times. And I think, our system was designed in such a way that we would kind of rely on having quick response times to be able to collect all the data that we're asking for. Let's say, we query the API for patient data for 100 samples at a time. Well, 100 samples times 30 seconds is a lot more than 100 times 3. So all of a sudden you end up, hitting Cloud Function time limits. And I think a way to maybe design around that, had we used a database, then maybe we would do something else, sort of a backup process perhaps that could occur on a schedule, and query their API for new patient data on a schedule, and then store that internally so that we know that we always have our data readily available. So that's something that, maybe we would think about differently if we were starting this over again.
Very cool. Eureka, you're muted.
Just talking away. So I have a couple questions for you. First, I wanted to know if someone who's watching or who sees this at some point, they wanted to get started with Google Cloud. What would you suggest as a starting point? How should they structure their how should they structure projects or things like that to kind of like get a good foothold in Google Cloud?
Yeah, so I'd highly recommend the Cloud Skills Boost. I can share a link to that at the end. So I sort of learned because when I started working at the Broad, Google Cloud was the provider that they use, and so I guess I kind of started with cloud storage buckets and then building upon that. So I think also, oh, thank you for sharing the link. I think starting with Cloud Skills Boost is great because it's probably going to start you off with some of those resources that are easier to understand and set up. So cloud storage, cloud functions. I think those are two great ones to play around with and get started. You can do something like dropping a CSV file in a cloud storage bucket and having your cloud function parse that file and then maybe write out a different file or create something in another cloud storage bucket. So just playing around with moving data through a miniature pipeline, perhaps, of your resources of choice is, I think, a nice first project. But Cloud Skills Boost definitely will have some suggested projects and things to try out. I think the Google documentation overall is really, really great for learning.
Thank you. And we do have a couple of questions in the Q&A right now. Hope, do we want to start with those?
Yeah, I do. Also, we will follow up regarding the slides content. It will likely be actually condensing it into an article. So just stay tuned for that. And that will be something so you'll be able to read and process everything later. For those that asked about that. And then we have a question from an anonymous participant asking, what kind of sequencing do you perform in the laboratory to obtain the polygenic determinants?
Okay, I'm super excited that someone asked this question because I actually didn't want to talk about it because I didn't want to get too much into biology, given, we're women who code cloud. But what we actually do is called array sequencing, or infinium arrays is the technology that we're using. And what we're doing really is not sequencing the entire genome, because in the case of polygenic determinants, we're only, like, we know in advance what regions of the genome we're interested in looking at for a specific disease. So when we run the arrays, we're just looking at certain regions, and the data we get back is only kind of giving us information on those regions in particular. So it's definitely a lot faster and inexpensive than full genome sequencing as well.
And how did you get started in this field?
Okay, well, I guess so. So my background is engineering physics. That was my undergraduate degree when I was in Canada, and part of the reason I chose that was because I was really interested in medical physics. And I thought, okay, the best way to do that at the university I was in, because we also didn't have biomedical engineering as an option at the time, but I really liked physics and was interested in medical imaging. So that was kind of my aim and what I thought I was going to do after graduating. But then over the last couple of years of my undergrad, I got really into software engineering, and I got an internship doing software over the summer in Cambridge, actually. And I really, really enjoyed it. At the time, that company I was working with had nothing to do with medicine, like the Broad, but I had, still that interest in me. So then I remember I'd be walking past the Broad on the way to my other job and thinking, wow, that seems like a really cool place. I wonder if they, hire software engineers. And so at some point I, looked into it further, and they do. Like, the Broad has a huge amount of engineers working there. And that really inspired me, and just finding out all the different things that you can do there as a technologist was really exciting. So I was kind of finally able to merge both my interests of working in technology, but coming back around to medicine.
A really cool origin story for how you got started there. We have another question in the chat. Stephanie asked, since you were able to collaborate with the folks responsible for the API, or were you able to establish service level agreements for the availability and responsiveness, et cetera?
I wish, Stephanie. That's a great idea, and something I would certainly like to press on more in the future for other collaborations. I think sometimes with research projects too, things are a little more loose in those expectations, because I think a lot more effort goes into like things like security that I mentioned and whatnot. So performance wasn't like our top priority, but yeah, certainly I think it's a great thing to consider when working with an API, whether you're the creator of it or not.
Lakshmi has a question, which is about your decision making in not using CloudDB. Was it only cost related, or did the data privacy have anything to do with that?
Data privacy actually didn't have anything to do with that decision because we had used cloud databases before for storing patient data. And so, with the right things in place and working with our information security teams, we have used things like Cloud SQL before. And that's yeah, and it's worked out nicely too. I think, yeah, the biggest consideration for us was just trying to keep costs low, because why not? And also to avoid setting up and maintaining a database. I think Cloud SQL, they do have things like automated maintenance, and it's pretty nice to work with. I've had good experience with it too, but it is just another kind of big piece to the puzzle. And it seemed like a bit of overkill for 25,000 samples.
We have a couple more questions. One is about you transitioning from physics to machine learning and AI. Can you talk about your path and how seems like it doesn't seem like the most linear path, or was it intentional? How did you?
Yeah, certainly my path was not the most linear, and I feel very lucky to have landed in software engineering, given that I don't have a software engineering degree. So yeah, I think the nice thing was, though, given my undergraduate degree was still in the Department of Electrical and Computer Engineering, we had the opportunity to take computer science classes, and like I remember using a lot of MATLAB for my physics classes too. So it is something that I got pretty comfortable with throughout my undergrad, enough that I was confident enough to apply to software engineering internships during my undergrad. And I think they're not always also looking for someone who has a computer science degree. I think it's about your experience, and maybe I did get lucky in that scenario. But I think there's plenty of people now applying to software engineering jobs that are also self-taught, and I think experience and getting that experience is the biggest thing.
Okay. So another question in the chat by an anonymous attendee was, do you think people without degrees can get into this profession at some level?
Yes, I do think so. It's harder because of course recruiters are looking for that, but I think things like boot camps for software development are gaining a lot of popularity, and a really nice way to learn a specific thing. I think that it's about kind of maybe choosing your niche too, right? Like if you love web design, well, maybe taking something on React and getting really good in React and is really powerful, instead of kind of trying to learn everything. And I think being really good at a few things is I think a good way to go when starting out.
I have a follow-up for that. Do you think that if a person isn't going the degree route, can they supplement with certifications and projects and things like that that would help them bolster those applications?
Yeah, definitely. I think in the case of like where I work, so the Broad Institute, I mean, there are sometimes minimum requirements. So if someone is applying for associate computational biologist, they usually need a degree for that, because that is they usually are, some of those I think even require a master's, but software engineers is kind of a different ball game. I've seen people come from all kinds of backgrounds, and I worked with one of my colleagues who she had a degree, I think, in geology, and then got into software engineering. So, it is kind of very open, which I think is great.
Yes.
I want to start wrapping things up, just keeping an eye on the time. I do have a question, which is, how do you see cloud technologies fitting in into the bigger picture of into the future of medicine and research? Do you have any personal?
Yeah, so yeah, I think it seems to be gaining more and more prevalence. Um, it's interesting because I think in a lot of medical systems, especially within hospitals, they use on-premises systems. And I think sometimes there's fear to change things, especially because it's patient data. I think, when I started out working in software engineering and it was a digital marketing company, they were putting everything to cloud. But I think when it comes to patient health information, there's always this extra sort of steps of caution that need to take place. And so I think some organizations can be very fearful of that, and understandably. So I think it's just a bit slower in medicine to see cloud coming out so strong, but I am seeing more and more of our partnering institutions and groups that we work with using cloud tools as well.
Very cool. There was a thank you for explaining your pathway and for the great presentation. Really enjoyed it. And what I would say is that for anyone that has any additional questions, feel free to reach out to Marissa on LinkedIn or reach out to us on the Women Who Code Cloud Slack. You can also join the general Women Who Code community. There's a career dev channel. So if you have questions about your path or more specific questions about either a specific pathway or uncertainties, there are lots of people that would be happy to ask or to answer your questions. And yeah, that was the question, the infinitum arrays. Okay, perfect. All right, so thank you so much, Marissa, for joining us. Thank you, Jarika, for hosting with me. And also, we'd love to have you back if you ever want to share more about your work with cloud and clinical data. This was really fascinating and also exciting. It sparks a lot of questions about the possibilities for the future. And I feel like with the pace of everything with cloud and AI, it is mind-boggling, but it is also exciting with all of the potential and the impact it can have. So thank you so much. We appreciate you being here, and we'll see you for the next technical talk.
Awesome.
Thanks,
Thank you so
everybody.
much for having me.